In this video, we are going to characterize a directional coupler that I have built. The directional coupler has 4 ports: radio frequency input port, radio frequency output port, the forward port and the reverse port. Some of the energy will be coupled from the main line to the forward and reverse port depending on how well matched the load to the generator is. If there's a perfect match, say 50 ohm, then a fraction of the energy will be coupled to the forward port and nothing to the reverse port. And if it's a perfect mismatched, either a short or an open circuit, then all energy will be coupled to the reverse port and nothing to the forward port. The first characteristic is the mainline loss. That is, how much attenuation will the main line produce from the generator to the load. We are going to use a nano VNA to do the measurement. Nano VNA will be coupled so that channel 0, which is essentially the S11 measurement port, will be coupled to the RF in port, and channel 1, which is S21, is coupled to the RF output port. Both forward port and the reverse port are terminated to 50 ohms. I have already calibrated the nano VNA for the frequency range from 100 kilohertz to 200 megahertz, and I have performed the open calibration, the short calibration and the load calibration, as well as the through calibration, which will be required for this measurement. The traces have been set up so that the yellow trace will represent the reflection from the input port as shown in logarithmic magnitude in dB. The green trace will be the input impedance as form of a Smith chart, the complex impedance, and the blue trace will be the output of the directional coupler, also in logarithmic magnitude. We can see that there is a very little attenuation in the main line, especially at lower frequencies. So, for example, at 24 megahertz, it seems like it has negative 0.03 dB, and the attenuation will increase somewhat at higher frequency. Let's say 162 megahertz would show something like -1 dB, so it's relatively small. Also, we can see that the impedance of the input port will also change as a function of frequency. So when the frequency is increased, we can see that the impedance will deviate from the nominal 50 ohm to some extent, but it's relatively close to 50 ohm at this frequency range. And the reflection from the input back to the generator is in class of -20 dB, -21 dB or so at the lower frequencies, and something like -15 at the higher frequencies. The next measurement would be the coupling from input to the forward port. This is the same arrangement as before. The only difference is that the channel 1, instead of coupling it to output port, is now coupled to the forward port, and the output and the reverse port have been terminated into 50 ohms. What we expect to see is the following. If we have V in as the input voltage from the generator and a turns ratio of N in the first transformer, then the voltage at the transformer secondary would be N times V in. And if we calculate the ratio between these two voltages and express it in dB, then it would be the secondary voltage, which is N times V in divided by V in, and taking the logarithm of that fraction, we find out that it will be 20 times the logarithm of the turns ratio, which will be approximately 26 dB in this case. So this is the test arrangement in practice. Now the blue trace represents the voltage at the forward port, and we can see that at lower frequencies it's approximately 26 dB down from the input, which was as expected, and the frequency being higher means that this forward coupling will also change, so that on higher frequencies it is something like negative 22 dB. And this is due to the fact that some of the energy will be coupled due to stray capacitances from the input to the forward port, and it will therefore change the theoretical value. The last measurement is the directivity measurement. It is the same as the coupling measurement, except that channel 1 is now connected to the reverse port, and both the load and forward port have been terminated into 50 ohms. This is the test arrangement for directivity measurement. I have changed the scale of the blue trace so we can see it more clearly. So at lower frequencies, say 32 megahertz, we can see that the directivity is better than 65, negative 65 dB, and as we can expect that the directivity will decrease when the frequency gets higher. So at higher frequencies it's something like negative 32 dB. This was an example of the measurements that you can do with the nano VNA. Hope you learned something. Thank you for watching.